At the National Archaeological Museum in Athens, behind a sheet of glass, lies a machine that appears to be impossible. It is not polished or complete. Most of it is missing. What remains looks like cracked slabs of green stone eaten by the sea. But X-rays have revealed 30 bronze gearwheels inside those fragments. Turn one lost handle, and the machine could follow the sun, reproduce the changing motion of the moon, identify possible eclipses, organize calendars, and track the cycle of the ancient games. It was made more than 2,000 years ago. How could a Greek craftsperson build it, who possessed the knowledge encoded inside it, and why did this technology seem to disappear? Its age is not a legend. Pottery and coins date the shipwreck that carried it to the final centuries before the Roman Empire. Its plates bear ancient Greek instructions. Its ratios come from Greek and Babylonian astronomy. Its gears are embedded inside the original marine corrosion. This is not a modern device hidden in an ancient site. It is decisive physical evidence that the accepted history of technology was incomplete. Yet no comparable geared calculator survives from antiquity. Nothing with this combination of compactness and complexity is known from the many centuries immediately after it. Much of what the machine did can now be reconstructed. Explaining how it became possible, and why it appears to have left almost no descendants, is the deeper mystery. The first clue did not arrive in a library or an observatory. It came from the bottom of the sea. Around Easter in 1900, a vessel carrying sponge divers from the Greek island of Symi encountered rough weather near Antikythera, a small, steep island between the Peloponnese and Crete. Sponge diving at the time was dangerous industrial work. Divers descended wearing heavy suits and metal helmets, connected to the surface by air hoses. They were not searching for archaeology. They were searching for a living. One diver descended near the island and found something unexpected on the sloping seabed. Ancient bodies seemed to be scattered below him. They were not human remains. They were statues, bronze and marble figures lying among broken pottery and the timbers of a wreck. The sight was extraordinary. With support from the Greek state and its navy, the divers returned and began one of the first major underwater archaeological recoveries. From a depth of roughly 45 meters, they raised sculptures, glassware, jewelry, pottery, furniture fittings, and other objects that had been carried on a large ancient ship. The most visually spectacular finds demanded attention. A bronze youth, marble figures, and fragments of luxury goods could be recognized immediately. A misshapen lump of corroded metal and wood could not. The lump went to the National Archaeological Museum in Athens with the rest of the cargo. Seawater had converted much of its bronze into fragile layers of corrosion. Wood from its case had survived only in traces. As the material dried and separated, something geometric appeared inside it. On May 17, 1902, archaeologist Vallejo Stares recognized a gearwheel in one of the fragments. That single observation changed the meaning of the wreck. A statue belonged naturally in the ancient world. So did an amphora, a coin, or a bronze couch fitting. A toothed wheel belonged there too. The Greeks knew simple gearing. But this was not one isolated wheel. More teeth and circular forms were visible beneath the crust. There appeared to be a system. The obvious explanation was also the least comfortable. The wreck carried some kind of geared instrument. The problem was that scholars had no established category for an ancient instrument of this complexity. Some proposed that it was an astrolabe. Others questioned whether all the pieces truly belonged together. The object looked too advanced for its context, and when evidence violates an accepted timeline, disbelief can feel more reasonable than revision. The mechanism offered a small but decisive reply. Its surviving surfaces contained inscriptions. Among the damaged Greek letters were calendar terms and references connected to the sky. This was not merely a set of gears. It was a machine with instructions. The German philologist Albert Rehm studied the fragments in the early 20th century and moved closer to the truth. He identified astronomical and calendrical language and proposed that the object was a calculating machine. That conclusion was remarkable because most of the internal structure was still hidden. Rehm had no computed tomography, no digital enhancement, and no three-dimensional model. He had damaged bronze, photographs, and words that could disappear into corrosion under changing light. Then the investigation slowed. The mechanism remained singular, incomplete, and brutally difficult to read. Wars and political upheaval interrupted scholarship. Some early notes were unpublished or scattered. Even the object itself continued to change as salt, air, cleaning, and handling affected its fragile layers. The machine had survived the sea, but survival did not mean stability. For decades, its public identity remained uncertain. It was famous enough to provoke speculation but too obscure to command a single explanation. The gears suggested engineering. The inscription suggested astronomy. The wreck supplied an ancient date. The missing pieces prevented the three from forming a complete picture. In the 1950s, a new investigator made the mechanism the center of a long campaign. Derek de Solla Price was a historian of science with a talent for recognizing what an object could mean beyond its physical size. He understood that if this machine really performed calculations through gears, it would alter the history of technology. It would show that ancient Greek theory had not remained only in diagrams and texts. Someone had translated mathematical relationships into moving metal. Price examined the fragments, studied their inscriptions, and sought ways to see beneath the corrosion. In 1959, he introduced a wider audience to what he called an ancient Greek computer. The term was provocative, but it was not meant to suggest electronics, memory chips, or programmable software. An analog computer represents quantities through physical relationships. In this case, the numbers of teeth on interconnected wheels embodied astronomical ratios. One rotation entered a date, the resulting rotations displayed calculated information. The machine did not think. It transformed. That distinction matters. A gear with 60 teeth driving one with 30 does not need to understand a 2-to-1 ratio. The ratio is built into the metal. Connect many wheels with carefully selected tooth counts, and a single input can produce several coordinated outputs. The machine becomes a physical argument. If the astronomical cycle is correct and the gears embody it correctly, the pointer moves to the answer. Price needed to know how many wheels were inside and how they connected. In the early 1970s, he worked with Greek nuclear physicist Charalampos Karakalos to examine the fragments using radiography. X-rays and gamma-ray images exposed forms hidden beneath the encrusted surfaces. The resulting evidence confirmed that the visible gear was part of a dense internal network. Price published his major reconstruction in 1974 under a title that captured the shock of the object, Gears from the Greeks. He interpreted the mechanism as a calendar computer and proposed a system of gear trains and dials. Some of his reconstruction was wrong. That is not a footnote to dismiss his work, it is part of the mechanism's history. Every generation has tried to solve a three-dimensional machine from distorted fragments, and every solution has been limited by the evidence it could see. Price had established the central fact. The object really was a complex ancient geared calculator. But knowing its category did not reveal its full design. Some gear counts were uncertain. Some shafts appeared to have functions that his model could not explain. The back of the device contained indications of spiral displays, yet their exact purpose was unclear. And the front, where the principal display had once been, was largely gone. The first answer had opened a larger question. If Price's reconstruction was incomplete, then what had the machine actually shown its owner? To answer that, researchers first had to stop imagining the mechanism as a modern clock. A clock divides a day into equal units. The Antikythera Mechanism worked on a more ambitious scale. It brought several different kinds of time into the same wooden case. The solar year does not contain a whole number of lunar months. The moon's speed across the sky does not appear constant. Eclipse cycles repeat, but not in simple annual intervals. Athletic festivals follow civic calendars. Planets sometimes slow, stop, and reverse direction against the background stars. The ancient sky was orderly, but its cycles did not fit neatly together. The mechanism was designed to make those mismatched rhythms visible. Imagine the original device before corrosion destroyed it. It was probably housed in a wooden case, often compared in scale to a mantle clock or a thick box. Bronze plates covered its front and back. Dials, pointers, and engraved text occupied the surfaces. A handle or knob allowed the user to drive the gears. Doors or cover plates may have protected the displays and carried extensive instructions. The owner did not wait for the machine to observe the sky. The user selected a date by turning the input. Inside, gear trains rotated at different speeds. On the front, pointers represented celestial positions and calendar information. On the back, pointers traveled through spiral scales that organized long cycles of months and eclipses. Every visible movement began with hidden arithmetic. This is where the title computer earns its place. The mechanism accepted an input, processed it through a fixed mathematical model, and displayed multiple outputs. It could be turned forward to examine a future date or backward to revisit a past one. It did not merely record observations. It generated predictions from stored relationships. But there is a trap in calling it the world's first computer. The phrase can make the object seem like a miraculous intrusion from modernity. In reality, every component belongs to its ancient setting. The bronze, the lettering, the astronomical theories, and the method of representing motion through circles were all available in the Hellenistic world. The achievement was not that someone violated history. It was that someone combined existing traditions more completely than the surviving record had led us to expect. The ratios inside the case provide the clearest evidence. One of the central problems in ancient calendrical astronomy was reconciling the moon with the sun. 12 lunar months are shorter than a solar year. If a calendar follows only 12 lunar cycles, its months drift through the seasons. Yet 19 solar years are very close to 235 lunar months. This relationship is known as the Metonic cycle, after the 5th century BC Athenian associated with it, although versions of the cycle were known in Babylonian astronomy. On the upper back of the Antikythera Mechanism, a pointer moved across a 5-turn spiral divided into 235 cells. Each cell represented one lunar month. The spiral was not decorative. It converted 19 years into a readable sequence of months, allowing the user to see how lunar and solar time could be coordinated. The pointer needed a way to follow the spiral without slipping into the wrong turn. Evidence suggests a small follower moved through a spiral groove, guiding the indicator across adjacent rings. This was information design as much as astronomy, hundreds of months compressed into a limited surface without making the dial impossibly large. Inside that larger cycle was another refinement. For Metonic cycles equal 76 years, a period associated with Callippus. A smaller dial counted that longer cycle. The machine therefore did not stop at a convenient approximation. It layered one correction over another. The lower back display addressed a more dramatic event. Eclipses do not occur at random, but neither do they repeat every month. The geometry of the Sun, Earth, and Moon produces patterns. One of the most useful is the Saros cycle, 223 lunar months, a little more than 18 years. After that interval, a broadly similar sequence of eclipses can recur. The mechanism encoded the Saros on another spiral dial divided into 223 cells. Certain cells contained abbreviated inscriptions. These glyphs indicated eclipse possibilities and supplied details such as whether the event was solar or lunar and at what time it might occur. This is decisive evidence. The machine was not simply an ornamental model of the heavens. Its maker committed specific predictive information to bronze. The word prediction, however, needs precision. The device could identify when the repeating cycle made an eclipse possible. It could not guarantee that an eclipse would be visible from the user's exact location. Visibility depends on geography, especially for solar eclipses. The machine calculated a cycle, not a modern local forecast. Even so, the result would have been powerful. Eclipses carried scientific, civic, and cultural significance. A machine that placed them within a recurring pattern transformed an event that could inspire fear into one that could be anticipated. The sky had not become less impressive. It had become mechanically legible. There was another correction built into the lower display. 3 Saros cycles form an exoligmos of roughly 54 years. Because the Saros includes an extra fraction of a day, an eclipse after one cycle occurs about 8 hours later. The Exeligmos dial helped adjust the indicated time across successive cycles. Once again, the mechanism did not merely state a pattern. It accounted for the pattern's drift. Consider what the user saw. On one side of the case, a pointer organized 235 lunar months. On another spiral, inscriptions marked eclipse possibilities across 223 months. Smaller dials tracked longer corrections. One hand turning at the side coordinated them all. Then the front display added a moving sky. The largest surviving fragment contains a prominent wheel about 13 centimeters across. Around the original front face were circular scales. One marked the zodiac, dividing the path of the sun into familiar signs. Another carried calendar information. Pointers moved over these rings, turning abstract cycles into positions a person could read. At minimum, the front showed the sun and moon. A small rotating black and white ball probably displayed the lunar phase. When the moon lay near the sun, the dark side faced the viewer. As the angular separation increased, the ball turned, showing a crescent, a half moon, and eventually a full bright face. The phase was not printed in a table. It emerged from the relative motion of the indicators. The moon presented a harder challenge than a simple circular pointer suggests. Viewed from Earth, its speed against the stars changes. Greek astronomers knew this irregularity. A pointer moving uniformly around a dial would therefore be visibly wrong. Inside the surviving mechanism is an elegant response, a pin and slot arrangement mounted on rotating gears. As one wheel turned, a pin moved within a slot on another, causing the output to accelerate and decelerate. The motion approximated the moon's varying speed. That detail is one of the most revealing in the entire machine. A basic calendar can be made by linking regular rotations. The lunar anomaly required the maker to convert a geometrical astronomical theory into variable mechanical motion. The gears did not merely count. They imitated. The model is often connected to Hipparchus, the great 2nd century BC astronomer who worked on roads. Hipparchus studied the motions of the sun and moon and developed geometrical models to account for their irregularities. The similarity makes a connection plausible. It does not prove that Hipparchus designed the machine, supervised its construction, or ever saw it. No surviving inscription names him as the maker. That boundary between plausible and proven is essential. The Antikythera Mechanism attracts famous names because it seems too important to remain anonymous. Archimedes, Hipparchus, and Posidonius have all been drawn into its story. Ancient texts describe impressive celestial devices associated with celebrated thinkers. But resemblance is not authorship. What is confirmed is more interesting than a famous signature. Someone understood a sophisticated lunar theory well enough to embody it in a compact mechanical device. That required cooperation between kinds of knowledge that modern institutions often separate: mathematical astronomy, metalworking, geometric layout, engraving, and instrument design. The mechanism's small games dial adds another dimension. Inscriptions identify a 4-year cycle and name major athletic festivals, including Olympia, Pythia, Isthmia, and Nemea, along with other regional games. The owner could connect celestial and calendrical time to events that organized public life across the Greek world. The Olympics were not an amusing extra added to a scientific instrument. Festival calendars helped structure travel, prestige, religious observance, and shared identity. A device that coordinated months and years could naturally show where a 4-year festival cycle fell. The sky and the city occupied the same machine. The names on that dial also created a geographic clue. Calendar month names elsewhere on the mechanism belong to the Corinthian family of calendars, with close connections to northwestern Greece and its colonies. The game's dial includes the Naya of Dodona and likely the Halia of Rhodes. These clues point in more than one direction. They may reveal where the device was intended to be used, where its underlying calendar came from, or which networks its owner moved through. They do not identify one workshop with certainty. For much of the 20th century, even this rear architecture remained only partly understood. researchers could see surfaces, trace damaged wheels, and compare possible gear arrangements. But the fragments concealed text and machinery under layers that could not safely be removed. The next breakthrough required a machine almost as remarkable, in its own context, as the object it examined. In 2005, an international research team brought advanced imaging equipment to the National Archaeological Museum. Hewlett-Packard specialists used a surface imaging technique that photographed the fragments under changing directions of light. By mathematically combining the results, researchers could emphasize shallow incisions that disappeared under ordinary illumination. Another team used microfocus X-ray computed tomography. The scanner produced high-resolution three-dimensional data from inside the corroded fragments. It could separate layers, reveal teeth, expose buried letters, and allow investigators to examine virtual slices through material that could not be physically opened. The machine that had once calculated the sky was now being calculated by another machine. The scans transformed the evidence. Researchers identified the surviving structure as 82 fragments, with 30 known bronze gears preserved among them. They read thousands of characters that had been hidden for approximately 2 millennia. Lines once dismissed as unreadable corrosion became parts of operating instructions, calendar scales, eclipse descriptions, and a catalogue of celestial motions. The inscriptions changed the investigation because they came from the artifact itself. Reconstructions can be elegant and still be wrong. A model may make the surviving gears rotate, yet add features that the original never possessed. The text places constraints on imagination. If an inscription describes a displayed planet, a successful reconstruction must explain how that display could have been driven. If it specifies a cycle, the gear train must reproduce the ratio. The back became substantially clearer after the scans. The Metonic spiral, the Saro spiral, the eclipse glyphs, and the game cycle could be tied to surviving mechanical evidence. The front remained the greater puzzle because most of its gearing had disappeared. Only about 1/3 of the original mechanism survives. That number should shape every confident image of a complete reconstruction. The missing 2/3 may have contained many of the wheels needed for the front display. A model of that lost system is therefore not a photograph of the original. It is a proposed solution to a constrained problem. The inscriptions supplied the most important constraint. They describe the Sun, the Moon, and the 5 planets known in antiquity: Mercury, Venus, Mars, Jupiter, and Saturn. They refer to cycles associated with those wandering bodies and to a front display arranged as a model of the Greek cosmos. The word planet comes from the idea of a wanderer. Night after night, most stars maintain stable patterns, but the planets shift against that background. Their behavior becomes stranger over longer intervals. At times, a planet appears to slow, reverse direction, trace a loop, and then continue forward. This retrograde motion is a consequence of observing other planets from a moving Earth, but Greek astronomers generally placed Earth at the center and explained the appearance through combinations of circular motions. That was not intellectual laziness. Without telescopes and without a modern inertial framework, a geocentric mathematical model could organize observations and generate useful predictions. The question for the mechanism's maker was practical: how could several circular gear motions reproduce a planet that sometimes moved backward? One answer is epicyclic gearing. A small circle can rotate on a larger circle, and a pointer attached to the combination can speed up, slow down, and reverse relative to the zodiac scale. The idea joins Greek geometrical astronomy to mechanical design with unusual directness. Modern reconstructions differ in how they arrange the missing gears. Michael Wright, a former curator of mechanical engineering at London's Science Museum, spent years examining the fragments and building physical models. He argued for a full planetary display and developed gear systems that demonstrated how ancient techniques could produce it. His work corrected important weaknesses in Price's reconstruction and returned hands-on craftsmanship to a debate sometimes dominated by diagrams. Later teams used the 2005 scans and newly read inscriptions to impose tighter conditions. A 2021 model led by Tony Freeth at University College London proposed a complex front arrangement showing the Sun, Moon, and all 5 planets on concentric rings. Its gear trains combined specific astronomical period relations preserved in the inscriptions. The result matched much of the known evidence and offered an integrated model of the missing cosmos display. It did not end the argument. No intact front gear train survives. Different researchers can accept the same inscriptions and fragments while preferring different mechanical solutions. The 2021 model is a major evidence-based reconstruction, not a recovered blueprint. Its authors describe a solution that fits the physical and textual constraints. Other specialists have questioned aspects of the gearing, manufacturability, and interpretation. That uncertainty does not reduce the mechanism to a blank mystery. The surviving text confirms that the planets were part of the intended display. The open question is precisely how the lost machinery produced their motions. One especially important clue is Fragment D. It contains a disc, a plate, and a 63-tooth gear whose role has generated competing interpretations. In a complete machine, that fragment may have belonged to a planetary train. Today it acts like a surviving sentence with its beginning and ending torn away. The words are real. The grammar around them must be reconstructed. The front display would have been visually dense. Concentric indicators likely carried small markers or spheres for celestial bodies. As the input turned, the planets moved around the zodiac at different rates. Some models reproduce their apparent reversals. The Sun and Moon maintained their own relationships, while the lunar phase ball rotated. The device compressed years of celestial change into motion under one person's hand. Yet its purpose remains less obvious than its functions. Its possible roles include research instrument, teaching device, luxury possession, demonstration of cosmic order, and portable reference for an educated owner. The inscriptions read in places like an explanatory manual, suggesting the audience needed guidance. The craftsmanship and density imply expense. The astronomical scope suggests more than a toy. But no surviving ancient invoice tells us who ordered it or what they paid. The mechanism may have crossed several categories that are separate today. A modern planetarium educates, predicts, entertains, and inspires. A precision watch tells time while also displaying status and craftsmanship. A scientific instrument can be a teaching object and a work of art. The Antikythera Mechanism could have embodied all of these roles. Its placement aboard the ship adds another unanswered question. The wreck carried a rich cargo through the Mediterranean during the 1st century BC. Much of it appears to have been traveling west, possibly toward Italy. The mechanism may have been merchandise, a diplomatic gift, private property, a collector's prize, or loot. The evidence does not choose among them. But the cargo tells us something about the world around the machine. By the time the ship sank, Rome dominated much of the Mediterranean. Greek artworks and intellectual objects were prized by Roman elites. Statues, luxury goods, and specialized instruments could move far from the workshops and communities that produced them. The mechanism was therefore not buried in the place where it worked. It was interrupted in transit. That interruption is why it survives. Bronze was valuable. A large obsolete or damaged instrument on land could be dismantled and melted into tools, vessels, fittings, coins, weapons, or another machine. Texts could decay, wooden cases could burn, and thin plates could be recycled. Underwater, the mechanism corroded almost beyond recognition, but the wreck protected it from the furnace. Its terrible condition is the evidence of its unlikely preservation. The same fact begins to answer why nothing comparable remains. We are not looking at a complete sample of ancient technology. We are looking at what burial, fire, reuse, chance, collecting, and excavation allowed to survive. Stone inscriptions and ceramics endure. Fine bronze mechanisms invite recycling. The archaeological record is not a neutral archive. It has material preferences. Still, preservation bias cannot by itself explain the mechanism's apparent isolation. If these machines were common, we might expect more fragments, tools, workshops, illustrations, or detailed descriptions. Some textual evidence exists, but it is indirect. The challenge is to decide whether Antikythera was the peak of a large industry or the exceptional product of a narrow specialist tradition. Ancient writers provide tantalizing parallels. Cicero, writing in the 1st century BC, described celestial devices that represented the motions of the sun, moon, and planets. One was associated with Archimedes, the mathematician and engineer from Syracuse who lived in the 3rd century BC. According to Cicero's account, the Roman general Marcus Claudius Marcellus took a sphere made by Archimedes after the capture of Syracuse. Cicero also described a sphere constructed by his contemporary Posidonius that reproduced celestial motions. These passages do not describe the Antikythera mechanism in enough technical detail to identify it. They do confirm that elite ancient audiences knew of mechanical models of the heavens. The idea was not invented by modern researchers trying to explain a corroded anomaly. Archimedes is an irresistible candidate because he united mathematics and mechanics and because ancient sources credited him with ingenious devices. But he died in 212 BC, and most proposed dates for the surviving mechanism are later. A tradition influenced by Archimedes is plausible. Direct authorship is unsupported. Posidonius worked on roads in the 1st century BC and was connected to astronomy, philosophy, and Roman intellectual networks. Cicero says he made a celestial sphere. That makes his circle relevant, but relevance is not identification. The mechanism contains no preserved line stating, Posidonius made me. Hipparchus fits another part of the evidence. His work on lunar motion resembles the theory embodied by the pin and slot system. He was active on roads in the 2nd century BC, within a possible chronological and geographic context for the device. Again, the relationship may be intellectual rather than personal. A later maker could use an astronomer's model without ever entering his workshop. The safest conclusion is also the one with the greatest historical consequence. The mechanism was not necessarily the solitary inspiration of one famous genius. It appears to draw on knowledge accumulated across regions and generations. The Metonic and Saros relationships had deep roots in Babylonian observation. Greek thinkers developed geometrical models that represented celestial motion through circles. Craftspeople possessed techniques for working bronze, dividing scales, engraving miniature text, fitting shafts, and cutting gear teeth. The mechanism joins these streams. Its maker was not starting from nothing. That makes the machine less miraculous and more important. A miracle can stand alone. A complex artifact implies a system. Begin with the metal. The surviving wheels are thin sheets of bronze, not thick modern gears machined from steel. Their teeth are generally triangular. The spacing is not perfectly uniform. Individual pieces were cut and finished by hand. Pins, posts, axles, plates, and supports held the layers together inside a compact case. To construct even one gear train, a maker had to choose the correct ratio, translate that ratio into tooth counts, lay out circles, divide their circumferences, cut dozens or hundreds of teeth, mount the wheels so they meshed, and control friction and looseness. Then the train had to fit beside and above other trains without collisions. An error at one stage could spread through the device. A wheel placed off-cent would change the contact between teeth. Uneven spacing could make the movement stiff. Too much clearance would introduce backlash, allowing a pointer to lag or jump when the handle changed direction. Too little clearance could make the train jam. The maker solved these problems without modern machine tools. That does not mean without tools. Greek and Hellenistic workshops used drills, lathes, compasses, files, saws, punches, and measuring instruments. Large geared systems were known in mills and lifting devices. Fine metalworkers produced coins, jewelry, surgical instruments, locks, and complex automata. Precision existed, though it was achieved by skilled hands rather than industrial standardization. The mechanism's inscriptions demonstrate another form of precision. Some letters are only a few millimeters high. They cover plates like a compact technical manual. Engraving that much information required planning, line spacing, abbreviations, terminology, and a sequence that corresponded to parts of the display. The words were not added casually after the gears were complete. Text and machine were designed to explain one another. This raises a practical possibility. More than one specialist may have participated. An astronomer could define the cycles. A designer could convert them into ratios and layouts. A bronze worker could manufacture the parts. An engraver could add the text. One exceptionally versatile person might have done several jobs, but the finished object contains enough distinct expertise to suggest a workshop environment. There is no confirmed workshop. There are no signed tools. There is no ancient instruction book showing how to cut an Antikythera gear. The system is inferred from the object's requirements. The distinction matters because the machine is often framed as evidence that ancient civilization possessed hidden industrial technology comparable to the modern world. It does not. One bespoke bronze calculator does not imply mass production, electricity, interchangeable parts, or a forgotten digital age. It proves something narrower and more defensible. Hellenistic specialists could build a compact, multi-output geared astronomical instrument of extraordinary sophistication. That achievement is large enough without exaggeration. The gears themselves preserve decisions. Tooth counts encode ratios chosen from astronomical theory. The rear displays organize long periods into spirals because circles alone would waste space. The lunar mechanism uses variable motion because a uniform pointer would fail. The inscriptions identify events, cycles, and celestial bodies. Every feature answers a problem. But one apparently simple feature has reopened the investigation in recent years: a broken ring of holes beneath the front calendar scale. For much of the modern study of the mechanism, reconstructions treated the outer calendar ring as a 365-day Egyptian calendar. Several Egyptian month names survive in Greek letters, supporting that interpretation. Small holes beneath the scale may have allowed the ring to be repositioned as the calendar drifted relative to the solar year. Only a fraction of the ring survives. Researchers therefore faced a geometrical problem: from the positions and curvature of the remaining holes, how many existed around the complete circle? In 2024, Graham Wone and Joseph Bailey of the University of Glasgow applied statistical methods associated with their work in gravitational wave astronomy. Their analysis found strong evidence for approximately 354 or 355 holes, closer to the length of a lunar year than a 365-day solar calendar. The result is not a trivial recount. If the ring carried roughly 354 divisions, then a major assumption about the front calendar display may need revision. The case also demonstrates why the mechanism remains alive scientifically. New questions do not always require a newly recovered gear. They can emerge from improved methods applied to measurements that already exist. The finding has not converted every scholar to one interpretation. It depends on reconstructing a complete circle from damaged points and on assumptions about how the ring was manufactured and mounted. Other analyses have produced related but not identical estimates. The confirmed fact is that the surviving segment does not preserve the total directly. The total is inferred statistically. Another recent challenge strikes at the machine's most basic reputation: whether it could turn reliably at all. In 2025, physicists Esteban Sigeti and Gustavo Arenas released a computational study combining models of triangular gear teeth with estimates of manufacturing error. Under their assumptions, irregularities could make gears disengage or jam frequently. Their simulation suggested that the mechanism, as represented by those measurements, might have been nearly unusable. The authors also stated the central limitation. The measured errors come from fragments deformed by roughly 2,000 years of corrosion, pressure, cracking, and conservation. The surviving shapes may not preserve the original geometry accurately enough. Their result produces two possibilities: either the device did not function as commonly imagined, or the original gears were more accurate than present measurements suggest. This is not evidence that the artifact is fake, nor does it erase its mathematical design. A non-functional prototype would still reveal sophisticated knowledge. But the question changes how we imagine the object. Was it a reliable working calculator, a demonstration model used carefully, a prestigious object whose concept outran its manufacture, or a damaged survivor whose original performance cannot be recovered from its present form? Physical reconstructions show that versions of the proposed gear systems can work when builders choose appropriate tolerances. What they cannot prove is that every missing detail matches the ancient original. A modern replica is an experiment; it demonstrates possibility, not identity. The most honest picture is therefore neither blind admiration nor fashionable debunking. The mechanism was designed to compute astronomical information. Its surviving gear trains embody real cycles. Its inscriptions describe a coordinated cosmos. How smoothly the original device operated remains less certain because the working surfaces have been transformed by the sea. The damage is not noise surrounding the evidence. It is part of the evidence. Look closely at Fragment A, the largest surviving piece. The green material is not simply bronze with a layer of rust. Much of the original metal core has disappeared. Information survives in corrosion products, mineral replacements, voids, impressions, and compressed layers. Conservation requires restraint because removing what appears to be crust can erase the shape of a tooth or the stroke of a letter. The object we call a machine is also a fossil of a machine. This explains why every confident reconstruction contains invisible decisions. A gear tooth must be counted where part of the circumference is missing. A shaft's purpose must be inferred from its neighbors. A line of text must be restored from incomplete Greek. A lost front display must be designed within the available depth of the case. Researchers test those decisions against several independent kinds of evidence. A proposed tooth count must fit the surviving arc. Its ratio must match an astronomical period named in the inscriptions. The wheels must occupy the available space, move the pointer in the direction indicated by the text, and rotate in a physical model without interference. When several constraints agree, confidence rises. When a reconstruction solves one problem by inventing parts that conflict with another, confidence falls. This is less like assembling a conventional jigsaw puzzle than rebuilding a clock after 2/3 of its pieces have vanished and the remaining pieces have fused together. The inscriptions are the voice of the missing parts, but even that voice is broken. The 2016 publication of a major corpus of the inscriptions brought together readings from the improved imaging. Researchers identified text on front and back covers, dials, plates, and fragments. Some passages function like captions. Others describe risings and settings of stars, eclipse characteristics, cycles, and the movement of the planets. The density suggests that the device taught the user how to interpret its display. One reconstructed line can change an entire gear train. Numbers associated with planetary cycles provide target ratios. References to color or motion can imply how a pointer or sphere appeared. A word located on a cover plate can help determine which face it explained. But damaged language invites overconfidence. Greek letters may survive only as partial strokes. Editors indicate restorations and uncertain readings. A smooth English sentence can hide the gaps present in the bronze. Any responsible story of the mechanism must distinguish between an inscription that is visible, a word restored with strong contextual support, and a machine element inferred from that restoration. That caution leads back to the most popular image of the device, a complete miniature solar system with nested rings and jewel-like planets moving around a central Earth. The image is plausible and supported in broad outline by the inscriptions. It is not confirmed in every mechanical detail. The Sun, Moon, and known planets belong to the described cosmos. The exact arrangement, number of rings, pointer shapes, colors, and gear trains remain partly reconstructed. A beautiful rendering can make uncertainty disappear more effectively than corrosion ever did. The surviving rear mechanism stands on firmer ground. Gear counts and dial divisions establish the Metonic and Saros systems. The pin and slot lunar anomaly mechanism is physically preserved. The game's dial is supported by inscriptions. These elements form the core of what the machine certainly or very probably did. The front planetary system is where evidence and engineering imagination meet. That boundary is not a weakness in the story. It is the story. For more than a century, the mechanism has forced scholars to move between object and model, each correction producing a better question. Rem saw a calculator where others saw an astrolabe. Price exposed a geared calendar but misread parts of the rear. Wright demonstrated planetary possibilities. The 2005 scans revealed instructions that no previous observer could see. The 2021 model answered many constraints while provoking new debate. Statistical analysis then challenged the assumed calendar ring. Mechanical simulations questioned the tolerance of the gears. The machine keeps changing without moving. Its date has also moved within a range rather than settling on one universally accepted year. The wreck itself is generally placed around the middle of the 1st century BC, often approximately 70 to 60 BC, based on cargo evidence including coins and pottery. The mechanism had to be built before the ship sank. Letter forms, calendar evidence, astronomical starting points, and eclipse patterns have produced proposed construction dates ranging across parts of the 2nd and early 1st centuries BC, with some arguments extending earlier. The National Archaeological Museum identifies it broadly within the Hellenistic period and describes it as an astronomical and calendrical instrument from before the wreck. Other scholarly reconstructions favor a date closer to 150 BC or later in the 2nd century. The exact year is disputed. This uncertainty does not threaten the central claim. Whether it was constructed in the later 2nd century or the early 1st, it remains an ancient Greek-geared computer from more than 2 millennia ago. Dating matters most when researchers try to identify its intellectual environment. An earlier date strengthens some proposed relationships and weakens others. A later date changes which astronomers could have influenced the design. But the name of one maker cannot be extracted merely by matching a date to a famous life. The calendar geography is equally complex. Corinthian month names might suggest northwestern Greece, Corcyra, or a related colony. The presence of games associated with Dodona and Rhodes broadens the network. Astronomical theory points toward traditions active in places such as Rhodes. Cargo movement points west. The shipwreck lies near Antikythera because of the voyage's end, not necessarily the machine's beginning. The evidence describes a connected Mediterranean more clearly than it describes one city. In that world, knowledge traveled through people, manuscripts, instruments, schools, ports, conquest, and patronage. Babylonian numerical cycles could be used within Greek geometrical models. A calendar from one civic tradition could appear in a device made or owned elsewhere. A machine constructed in a Greek workshop could be carried on a vessel serving Roman demand. The Antikythera mechanism is often treated as an object out of time. It may be better understood as an object made possible by movement across its time. That movement also helps explain the level of synthesis. Babylonian astronomers accumulated long records and developed powerful arithmetic methods for predicting recurring phenomena. Greek mathematical astronomy often sought geometrical accounts of motion. Metalworking traditions provided physical techniques. The machine did not choose between numbers, geometry, and craft. It made them cooperate. The Saros dial is Babylonian cyclic knowledge expressed through Greek letters on a bronze spiral. The lunar anomaly is geometrical theory expressed through a pin sliding in a slot. The calendar and games dials connect scientific cycles to civic life. The result is not one culture's isolated flash of genius. It is a compressed Mediterranean history of knowledge. And yet, after the ship sank, the trail seems to go cold. No surviving object from the next several centuries matches the Antikythera mechanism's complete combination of densely packed gears, astronomical cycles, spiral dials, variable lunar motion, and extensive instructions. Much later, Byzantine and Islamic instruments show that geared calendars and celestial mechanisms were not conceptually impossible after antiquity. Medieval astronomical clocks eventually reached comparable and greater mechanical complexity. But there is no documented production line carrying this exact design intact from the Hellenistic workshop to those later machines. The disappearance was probably not one dramatic moment. Technologies can be lost without anyone burning the final blueprint. They disappear when the network that sustains them becomes thinner than the knowledge requires. A device like this needed more than an inventor. It needed patrons willing to pay, astronomers able to supply models, craftspeople trained to cut and fit small parts, engravers who understood the layout, and users who valued the result. If demand declined, a specialist retired without a pupil, a workshop closed, or text stopped being copied, the chain could break. Each individual skill might survive while the particular combination vanished. The political world also changed. Hellenistic kingdoms gave way to expanding Roman rule. Centers of patronage shifted. Libraries, schools, and workshops endured in some places and suffered in others. Later crises altered trade, cities, institutions, and education. None of this proves a single cause for the mechanism's disappearance. It explains how an expensive, specialized tradition could fail to reproduce itself. Material value completed the erasure. A thin bronze plate did not look like sacred knowledge to someone who needed metal. It looked reusable. A broken gear could become part of a vessel. A case could become fuel. Instructions engraved on bronze were safer from ordinary decay than papyrus, but only until the plate entered a furnace. The result is an illusion created by survival. We see one machine, followed by an apparent emptiness, and imagine one impossible leap. The more reasonable inference is that the machine had predecessors and perhaps companions because its design is too integrated to look like a first attempt. But that inference must remain an inference. No earlier complete geared astronomical computer has been found. The mechanism therefore proves a tradition existed at least once, not how large that tradition was. This is the central reversal. The machine should not exist only if the archaeological record is assumed to preserve the upper limits of ancient ability. It does not. Archaeology preserves a filtered residue. The Antikythera wreck happened to trap one object beyond the reach of recycling, then conceal it until modern divers arrived. The sea nearly destroyed the machine and saved the evidence of its existence at the same time. That paradox continued after recovery. Had the corroded lump remained intact, the gears might have stayed unseen. When it cracked, the damage exposed a wheel. Later, non-destructive scanning recovered information from the corrosion that physical cleaning could have erased. At every stage, destruction and discovery were separated by millimeters. The human chain is equally fragile. A sponge diver recognized statues where he expected a natural seabed. Vallejo Stars recognized a gear where others saw an encrusted fragment. Albert Rem recognized calculation in broken words. Derek de Solla Price recognized a computer in a machine he could not fully reconstruct. Carolampos Caracalos helped see inside it. Michael Wright tested theories with working metal. International teams used light and X-rays to recover instructions. Epigraphers reconstructed letters. Astronomers checked cycles. Engineers challenged tolerances. No single person solved the mechanism because there is no single version of the problem. To an archaeologist, it is cargo from a wreck. To an epigrapher, it is a damaged Greek text. To an astronomer, it is a collection of period relations. To an engineer, it is a transmission with severe spatial constraints. To a conservator, it is unstable mineralized bronze. Every discipline can expose a mistake made by another, and every genuine solution must survive all of them. That is why the mechanism has taken more than a century to decode and remains unfinished. The difficulty does not come from a magical secret hidden by its maker. It comes from the amount of ordinary information that has been lost: the missing wheels, the erased letters, the vanished case, the absent handle, the unknown owner, the unrecorded workshop, and the unpreserved instructions for manufacture. The machine's modern fame can also distort its ancient meaning. We celebrate it because it resembles a computer. Its maker may have valued something different. To an ancient user, the most astonishing feature may not have been calculation as an abstract achievement. It may have been the ability to hold the order of the heavens in both hands. Turn the handle, and a month advances. Continue, and the moon changes phase. A pointer approaches a cell marked for an eclipse. Another dial moves through the cycle of games. On the front, wandering lights travel through the zodiac, sometimes changing speed or reversing. Decades pass in minutes, but the relationships remain. The device makes time tangible. It also reveals a particular confidence about nature. The sky could be represented because its apparent complexity contained patterns. Those patterns could be expressed as numbers. Numbers could be converted into ratios. Ratios could be cut into wheels. Wheels could move pointers. A prediction that began with generations of watching the sky ended with a person turning a handle. That sequence is the machine's true technology. The bronze is only its final layer. It explains why calling the Antikythera mechanism an ancient computer is useful, provided the phrase does not erase its difference from a modern one. A modern computer can be reprogrammed for countless tasks. The ancient device was dedicated to one model of cosmic and calendrical order. Its program was fixed in tooth counts. Its data were astronomical periods. Its display was a set of physical pointers. Its power source was a human hand. What it lacked in flexibility, it gained in transparency. The computation was visible in principle. Open the case, and the mathematical relationships were material objects. A ratio had a diameter. A cycle had a spiral. An irregularity had a pin and slot. There is no evidence that the mechanism gave its owner supernatural knowledge. It did not discover new planets, measure longitude at sea, or open a path through time. It could not escape the limitations of the astronomical theories encoded within it. A beautifully geared model could still produce an imperfect planetary position if the underlying model was imperfect. That limitation makes it more human, not less impressive. The maker built the best available understanding into bronze, including both its insight and its error. The same is true of every modern reconstruction. Each one freezes the best available interpretation at the moment it is made. Then a hidden inscription, a revised tooth count, a statistical analysis, or a mechanical test exposes what the model missed. The history of decoding Antikythera is a sequence of intelligent errors becoming narrower. The unanswered questions are now specific. Researchers do not need to ask whether the artifact contained gears, the gears are there. They do not need to ask whether it handled astronomical cycles, the ratios and inscriptions confirm that. They do not need to ask whether it could identify eclipse possibilities, the Saros dial establishes that function. They still ask how the lost planetary gears were arranged, what the complete front looked like, whether the calendar ring contained roughly 354 or 365 divisions, how accurately the original wheels were made, how smoothly they turned, when the mechanism was calibrated, where it was built, who commissioned it, and whether more fragments remain near the wreck or unrecognized in storage. Each question has a path to evidence. Another fragment could preserve a gear. Improved imaging could separate overlapping letters. Better models could test manufacturing tolerances. New excavation at the wreck could clarify cargo, route, or ownership. Comparative discoveries could reveal whether this machine belonged to a family. The possibility of a second mechanism is the most consequential. One comparable artifact would change the problem from biography to industry. Shared tooth counts or inscriptions could identify a design tradition. Different calendars could show adaptation for different clients. A simpler predecessor could reveal how the architecture developed. Until then, Antikythera remains a sample of one. That sample is enough to overturn an old assumption but not enough to replace it with fantasy. Ancient craftspeople did not possess modern technology in secret. They possessed their own technology, and parts of it were more sophisticated than the surviving record once allowed historians to see. The mechanism did not arrive from outside history. It came from Babylonian observations, Greek mathematical models, Mediterranean workshops, civic calendars, athletic festivals, elite patronage, and the practiced hands of people whose names are gone. Its apparent impossibility is created by everything around it that failed to survive. So how could the ancient Greeks build a 2,000-year-old computer, and why did it disappear? They built it by joining generations of astronomical knowledge to a highly specialized tradition of bronze craftsmanship. It disappeared because that combination was rare, expensive, vulnerable, and preserved in materials that later generations had every reason to reuse. The knowledge did not need to vanish in one catastrophe. The chain only needed to break. What survives in Athens is not the machine as its owner knew it. The wooden case is gone. The handle is gone. Most of the front display is gone. The colored celestial markers, if they existed, are gone. 2/3 of the mechanism is gone. Even much of the bronze has been replaced by corrosion. But one relationship remains locked inside the fragments: a human hand once turned a wheel, and the heavens moved.